Myself, GOWRI, and I am a member of the group Chemistry. Our members were Srushti ma'am, Sneha ma'am, and Niyati ma'am. And my fellow group members are Abhijeet, Raghvendra, Mahi, and Suyash. Problem statement. A microscopic analysis of gold nanoparticles, a secondary crystalline structure for self-healing properties in line with their antibacterial properties, electrical and mechanical self-healing method, and advanced application in biotechnology. Abstract. Self-healing gold nanomaterials, which are made by incorporating nanoparticles of gold into polymers or gels, possess an intrinsic and self-sensing mechanism of self-healing at the nanoscale. This takes advantage of the superior conductivity and stability of the gold material to allow for assignment of two leading healing mechanisms: the reversible metal ligand bond, which will reform under certain principles, and plasmonic heating, in which localized heat for crack repairing can be produced through nanoparticle absorption of light. The materials may offer scope for applications in, for instance, flexible electronics, sensors, and biomolecular devices because of potential improvements in the toughness of the device, minimization of maintenance, and an increase in the precision of the application. There is increasingly more attention dedicated to developing room temperature heating for quicker, more efficient and scalable applications in sustainable tech and biomedicine.
Next, I will be discussing about gold nanoparticles. Generally, the size of gold nanoparticles are very small, due to which they have some unique properties like optical, electronic, and thermal. These properties help them in medicine, diagnostic, drug delivery, and photothermal therapy. And they also have been research regarding environmental applications and technological applications in biosensing and catalysis. Structure of gold nanoparticles. Gold nanoparticles have a core which is made up of gold atoms, which is commonly in an FCC crystal lattice. The arrangement of atoms at the surface of gold nanoparticles may deviate from bulk due to size deviation, which is generally between 1 to 100 nanometers, and play a huge role in electronic, optical, and chemical characteristics.
Now I will be discussing process of self-healing. First topic, interaction of sulfur-gold particles. Sulfur-gold interaction can make the structure of gold nanoparticles extremely strong. The bond between sulfur and gold can be switched on and off using an NIR laser due to the optothermal properties of GNPs. When these interactions are switched off, the GNPs can reconstruct the damaged areas, giving rise to the self-healing properties. These self-healing properties are used in hydrogels and conductive elastomers. Hydrogels are used in wounded areas to ward off microorganisms and to facilitate healing of the wound. Conductive elastomers help heal wearable sensors and other highly sensitive parts of electrical devices. Polystyrene and gold nanoparticles. Gold nanoparticles can be made as hybrid films with polystyrene with high photothermal healing behavior. These films can be used in devices with high photon energy sources. However, the transparency and flexibility of the gold phosphorus film is highly dependent on amount of gold nanoparticles. Synergistic interactions. This refers to the interaction of sulfur-containing polymers and gold nanoparticles, the mechanism, stability of resulting materials along with their healing properties.
Properties of gold nanoparticles. First, optical properties. Gold nanoparticles exhibit unique optical properties due to surface plasmon resonance, where conduction electrons oscillate in response to light, leading to strong light absorption and scattering. This gives color ranging from red to purple, influenced by particle size, shape, and the surrounding medium. Their tunable SPR across the visible spectrum makes them valuable for applications in biosensing, imaging, drug delivery, and as contrast agent in photothermal therapy. Second, thermal properties. Gold nanoparticles have unique thermal properties, including high thermal conductivity and efficient heat transfer, especially enhanced by surface plasmon resonance. When exposed to light, particularly near infrared, gold nanoparticles effectively convert absorbed photons to heat, making them effective for photothermal cancer therapy. Their small size and high surface area enable rapid thermal response and dissipation, beneficial for heat management applications. Additionally, gold nanoparticles exhibit thermometric stability, maintaining their properties in variable conditions.
Due to their small size, GNP shows antibacterial properties. When they are exposed to light, it generates reactive oxygen species which enhance the antibacterial effect. And AUNPs are functionalized with antibiotics and peptides to improve their antimicrobial activities. Such properties make GNPs effective for bacterial growth, prevention of bacterial growth, and effective for treating infections. Fourth, electrical properties. AUNPs are excellent electrical materials because of the high electrical conductivity. AUNPs are also functionalized with organic materials. AUNPs retain electrical conduction properties on reduction to the nanoscale and with a high prospect of nanoelectronics, sensors and conductive cells. They present an efficient electron transfer, making them more efficient in field, effective transistor and molecular electronics.
Fifth, mechanical properties. Gold nanoparticles have unique mechanical properties because of their small size and high surface area. But the bulk gold is soft and ductile, whereas gold nanoparticles are much harder and stronger due to their reduced dimensions and the influence of surface atoms. The mechanical behavior of gold nanoparticles is generally sensitive to their size, shape and surrounding environment. They are stable at nanoscale against deformation and were known to exhibit behavior characterized by a size-dependent elastic property, which is catalytic property. The catalytic activity of gold nanoparticles is significant in small size reactions, including hydrogen, carbon monoxide and organic molecules. The gold metal itself is inert as a bulk material but finds high catalytic activity when arranged as a nanoparticle due to large surface area and high surface energy along nanoscale interactions of reactants. These properties make gold nanoparticles precious materials for the application of green chemistry, environmental application and energy conversion processes such as fuel cells.
Mechanisms of self-healing. The first mechanism we are going to talk about is reversible bond mechanism. Reversible bonding in self-healing gold nanoparticles involves dynamic chemical bonds that break and reform to repair structural defects. These bonds, which can be covalent or non-covalent, allow damaged particles to reassemble in stress conditions like heat, pH changes or redox reactions. When these bonds break due to stress, atomic or molecular mobility allows for rearrangement and the bonds reform once their conditions stabilize. This mechanism helps GNPs maintain their structure and functionality, making them more durable and robust for applications such as catalysis, drug delivery, and testing. The next mechanism we are going to talk about is plasmonic heating mechanism. Self-healing of gold nanoparticles through plasmonic heating occurs with localized heat generated by the excitation effect of plasmons. When specific wavelengths of light hit GNPs, electrons oscillate, producing heat around the nanoparticle. This localized heating enhances atomic mobility at the surface, allowing atoms to move towards and prepare damaged areas. The precise and controlled heating mechanism ensures that only the illuminated area generates heat, making it beneficial for applications such as catalysis and drug delivery, where structural integrity and stability are crucial in changing environmental conditions.
Uses of nanomaterials in different industries.
Use of GNPs in healthcare and medicine. They are used in drug delivery systems. The drugs target the cells so that they may result in greater efficacy than the conventional drug therapies without adding any burden to the patient. They are specially used in cancer therapy. They are used as coatings to avoid infection. They are applied to all medical equipment in hospitals as they kill the bacteria. Second, textile and consumer goods. They are used as antimicrobial fabrics which are applied to sportswear and medical textiles. Also used in sunscreen which helps UV protection and are also used in smart textiles. Third, food and agriculture. They are used in food packaging that increases the lifetime of food products and used as nanosensors in packaged food alerts about spoilage and contamination. And for crop growth, plant, nutrient uptake by plants and crop disease resistance nanomaterials are used?
Fourth, construction and building materials. In cement and concrete, nanosilica particles improve concrete by enhancing its strength, durability, and crack resistance, which is essential for extending the lifespan of infrastructure. While in fire-resistant materials, nanomaterials can be incorporated into building products to create fire-resistant nanocomposites, making them ideal for safer application in public and residential buildings. Fifth, environment application. Nanomaterials enhance environmental protection through various applications. Nanofilters and photocatalytic nanoparticles purify water by removing heavy metals, organic pollutants, and bacteria. Carbon nanotubes and nanofibers improve air filtration for industrial and urban air quality. Nanosponges are highly effective in cleaning oil spills. And environmental sensors with nanomaterials enable real-time detection of pollutants and toxins in industrial and environmental settings.